Let's start with this section-based recommendation system. This work is trying to diversify the items. So this work aim to diversify the diversities of the items recommended to the users. So one typical problem in recommender systems is some items the recommender systems recommend are repeated or duplicated. So one example here is someone buy milk or bread online. Maybe they may again recommend the bread or milk, but what the customers want may be the ham. So this is what we're trying to solve in this problem. And so the non-IIDness here is in general, some users choice are often somehow dependent on their previous choice in a purchasing section, which means just like the example here. So people buy the milk and bread, so the next choice may have some kind of relation to the items purchased here. So if we can take into account of this context to make the recommendation, the recommended items may be more sensible and relevant. And so the choice of items when we do make purchase in sections, the items we put into the bracket may follow some sort of order, but it's not very rigidly order sequence, but there are some sort of orders there. I will present later how we make use of this kind of order in our model. This work is inspired by the distributive representation hypothesis. In NLP, the most famous one of the most famous representation models, what to wear, the hypothesis is the words I know by the context they occur. So they use the context to the context of a specific word to predict to see the probability or the posterior of given this context of having this word. So this is quite similar into our problems we want to solve. We want to recommend or relevant items based on the items we purchase in a current section. So this is analogies here. And another analogy here is the number of items we can recommend, and the size is as large as to the number of words in a vocabulary. So these two analogy inspire us to introduce these 3-layer serial white in, white out networks. So these networks, so in general, you can see here, we want to have two kind of embedding. One is the user's embeddings on the left-hand side, and the context embeddings on the right-hand side. And we want to use these two embeddings as the conditions to predict the probabilities that a user purchase this target item B. And more specifically, in the left-hand side, this is one-hot embedding, one-hot encoding of the users. So the one-hot encoding here is the length of the vector here. This one-hot embedding vector here is equal to the total number of users in the database. And the one-hot embedding means only for specific user. So only that users will be one in the cells here, and all the other users will be 0. So this is what we use the one-hot embedding. And after getting the one-hot embedding, we use some sort of sigma function to mapping this one-hot embedding into this user embeddings. The function we use is the nonlinear logistic mapping. So by using such kind of mapping function, we mapped one-hot embedding into a lower dimension user embeddings. So similarly, on the right-hand side, it is the items one-hot embedding. So in a purchase section, if the section have C items, then we will have C item vectors here. So each item vectors is also a one-hot embedding. So this will result in a problem. The length of the one-hot embedding of the items is not equal. So in order to solve these problems, before doing this encoding, we first concatenate all the one-hot embedding, concatenate all the sections together, and then do the one-hot encoding, which means the one-hot item vector has the length as the same as the total number of items in the whole dataset. So by doing this way, all the item vectors has the same length. So this will facilitate us to use the same mapping function here to gain the item embedding, which is HV here. So this HV, because we want to gain context embeddings rather than a single items. So we have a weighted summation here. So the metric here is how can we properly determine the weight for each items in a section. The way we did is that, so if an items is more closer to the target items, we want to assign a higher weight. So if our items is far away from the target items, we consider it is items that is less dependent on the target items. So we use an exponential decade functions to specify these weight functions. So this is different from the word-to-vec, because the word-to-vec they have a specific sliding window size. Here we only use an exponential decay function to capture the dependencies between the neighborhood items and the items far away from the target items. So after we get all these two user embeddings and context embeddings, we will integrate them together to make a prediction of the target item T. So this is the top upper layer is the soft mask layer, and so all these two layers are a fully connected layer. And so by solving these problems, so for each users, they will get a list of target items, which is the probabilities that this user or given user, the probability that this user having interested in the target items. So this will output a ranking of items. So this will be similar to the traditional recommendation problem. So we can simply recommend the top K items. And so it is also obvious here is that one straightforward variant of this framework is that we can only use the context embeddings. So just remove the left-hand side, we'll get another framework. So we will show in our experiment results how this will make the contribution to the final prediction result. So the previous one that does not show how we link the user embeddings and the context embedding together to make the predictions. So here you can see here we have a summation together to get the scores of a given user and its associated context. So these components indicates that we want for given data, we want to sum all the prediction together to make construct the objective functions. So after make a log likelihood, we will have distance. This is similar in the to web. And so the problem here is also similar. So the challenge here is how to compute this big component, the log z, because I just mentioned, the total number of the items can be very large, and for each training examples, we always need to compute this very large term. This will result in a very costly computational time. And so the traditional way to solve it is use the NEC, the noise contrastive estimation. So the NEC work in this way. We assume a noise distributions Q, and we want to randomly drop K noise examples out of these distributions. Then we can formulate these two probabilities. One is the target item or the target word is drawn from the normal data distribution. The probability is something like this, and similarly we can get the probability that the sample is drawn from these noise distributions. So sum them together we'll have the log likelihood equation here. So the key problem here is always the how we generate the noise distributions. And the way we did is that this distribution, we make it proportional to the frequency of the items, which means that the more frequency and items occur in the entire data sections, the more likely it will be chosen as a noise example here. So the rationale under this noise distribution generation is that because very popular items are usually less dependent on the other section items because they are very popular. Every user buy these items, which means they don't have any association. They have much less dependencies on the other items. Yeah. So far we have already solved all the components here, and so we after cracking the equation, this score equation into here, we can use the gradient descent to work out these problems. We did some experiments on this each type dataset. It is a real-world dataset from Timor, and it's a quite big dataset. A couple 6 months shopping log. And so the problem when we design the experiments is that how do we creating the testing sets? So we design 2 ways to creating the testing sets. One way, the last strategy is that for each user sections, we use the last items as the ground truth, which means all the previous items used as the context. So this is the one strategy we use. Another strategy is the leave one out strategy. So this means that for sections have k items, we will create k testing examples, because for each items we leave it out and use the rest of k-1 items as the context and do the predictions. So it also results in a very different numbers of examples in the testing set. We compare with several competitors, some baselines, and also some very recently proposed deep iron-based methods. And so this SWIWO is the full models as I presented before. This with a DSI is the models. They only models the item section context. So we did not consider the user embeddings in this model. So we will see the difference when we so this is the one use only the items the context embeddings. This use the context embeddings as well as the user's embeddings. It is clear to see that both models performs better than the competitors we use here, and in terms of different measures here, and the difference here is quite substantial. So, which means we just justify what we assumed before, that considering the section context can help us to make more sensible, relevant recommendations. And we conduct another set of evaluation here, because as we argue in the very beginning, we want to recommend very diversified items. but we also want to keep the accuracy of these diversified recommendations. So the two metrics we use here is one is the diversities here. So the diversity measure the non-overlappings between each pairs of recommendations is calculated in these ways. Another is F1 at the top case. This F1 scores is different from the traditional one because we replace the procedures with diversities. So we want to examine whether we can improve the diversities without losing the accuracies. So this is the results we obtained. It's clear to see that we have our two models here have better diversities than the baselines and some state of the art. But at the same time, we also have improvement in the accuracy. So this is a quite impressive result we obtained. Next, I will introduce some work in the non-IID outlier detection. So after I introduce some backgrounds, I will go into the non-IID value-based approaches and also the from value to feature hierarchical coupling-based approaches. So some background here is that we recently only focus on the multidimensional data. As you may know, there have been many work on other typically non-IID data, such as the graph data, the sequential data, and some other typical non-IID data. But for multidimensional data, very few work actually considering the underlying non-IID issues. So this is some popular methods in the domain of outlier detections. So most of them have the IID assumptions here. So they may assume that either the values or the features or objects from homogeneous distributions or mechanisms, and they are also implicitly to assume the independence between these entities. So you can see the example here. The distribution is very different. So, but the traditional one does not consider such kind of heterogeneities. I give you some more non-IID examples in our real life data, such as the interdependencies of couplings. So consider the case in the diabetes science. So, according to some official websites, a person who have diabetes type 2, they often have at least 3 or 4 or more signs of this. So some is frequent urination or weight loss or lack of energies and thirsty. So this kind of concordance indicates there are some sort of interdependencies between those signs. And another one is the heterogeneities here. So this is only 4 features from a very popular dataset, the couple type. So you can see the distribution here is very different. So I give you one simple example that why we need to consider the non-IID in our traditional multidimensional data set. So this is the AUC performance using the KN, but with very different distance. So this one is using the traditional Euclidean distance, but the blue line is using the standardized Euclidean distance. This is standardized by the standard deviations in each features. So which means the blue line somehow consider some kind of heterogeneities in the data sets. So with this take this into consideration, we so just simply have more than 6% AUC improvement. I will present you more examples show that when after considering this non-IIDness in outlier detections, we have very substantial improvement. This is what the mammographic data look like. You can see the first 3 data feature distribution is very different from the later three ones. Next, I will present you some methods they try to capture the complex interactions at the value level. This work was published in IIDkai 2016. The motivation here is quite straightforward. So for the value heterogeneities, you can imagine for different frequency distributions, we are still talking about working on the categorical data here. So given two features, if one feature's frequency distribution follows some sort of normal distributions, but another feature, its frequency distribution is following some sort of power very long tail distributions. Under these 2 different types of distribution, even you have values in these 2 features have exactly the same frequencies, but such kind of frequencies have very different semantics because they have very different context there. So, but in the traditional categorical data outline detection, they simply assign the same outliners with such kind of values, but you can very straightforward to sense their semantics is very different. And for the another perspective is the value couplings. So this is also similar to the word-to-word or the sentence-based recommendation. So in outline detection, it means that an behavior or feature value, how outlying it is, it quite depends on the values it co-occurs. So take an example here. If someone who just has some sort of weight loss, but do not have the other signs, that does not make a lot doubt on whether these persons have diabetes. But if the person also have the signs of satiety and dryness and frequent urination, then the behavior or the value of heavy weight loss is very likely to be an outlying behavior. So this is what we consider the concurrent outlying behaviors. such kind of concurrent behaviors has the result that then one value's outlierness is dependent on the outlierness of its accompanied values. Here we try to introduce a framework to model this such kind of non-ID values. The framework is working in this way. So, firstly, we introduce an intra-feature outline factors. These intra-feature outline factors capture the intra-feature frequency distribution heterogeneities. And this inter-feature outline factors is to capture the homophilous dependencies between the values. The homophily is the one value's outlierness is dependent on the outlierness of other values. So after obtaining these two factors, we propose a model to unify these two factors together to make to estimate the value outlierness. So this is also one key difference from our frameworks to the existing frameworks. We are focusing on learning the value outlierness rather than what the popular paradigm is, the pattern based, because we are working on the categorical data. So due to the discrete nature, so most of existing work just to try to find the frequent pattern as normal pattern or other infrequent patterns as abnormal patterns, and use the pattern outlierness to calculate the data objects outlierness. The benefits with working on the value level outlierness is that we can capture much more complex interactions at the value level. If we considering on the pattern level, it is much more difficult to have a comprehensive modeling of such interactions. Another benefit of learning the value outlierness is it has very good flexibility in terms of the applications. So because the value is the very lowest levels, so we can use the value outlierness to infer the outlierness of data objects, and as well as the outlining of features. We even can have other applications, such as use it to explain why an object is an outline. For the intra-feature outline factor, so the motivation is here. So a value of the same frequencies in different features may have very different semantic. Semantic here is they have very different outlierness. And in order to capture this difference, we use a normalized way to calculate the value outlierness within each features. So given a value in the feature F, we first find the mode M in these features, and to calculate compute the outlierness of the mode. So this mode is used as a benchmark there. So each feature will always has a mode. And then based on the value frequency deviation from the mode frequency, we have another outlierness. We have the average over this to obtain a intra-feature outline factor. So the benefit here is we consider the intra-feature frequency distributions. We use the location parameter here to address the heterogeneity. And in inter-feature outline factors, we define the interfeature outlier factor to capturing the homophily value couplings. So the homophily is reflected by the high mutual conditional probabilities. But the question here is why the conditional probability of real values or abnormal values, they have high conditional probabilities. The answer here is that because the outlying values, they often have very low frequency. They have very low frequencies, and as I mentioned before, they tend to be concurrent together. So they have join, even though they have very small join probabilities, but due to they have small marginal probabilities, so as a result, they have high mutual conditional probabilities. This is the one key properties here to enable us to capture these homophily couplings between the outlying values. After obtaining these two outlier factors, we use the graph-based ways to integrate them. So first, we map these two outline factors into a value-to-value attributed graph. Attributed means we for each value, for the graph here, each node is a value, and we use the intra-feature outline factors as these nodes node properties, one-dimensional information here. And for the edge between any two values, we use the interfeature outline factors here. So when we calculate the transition probabilities from, for example, from V32 to the V22, we will have this kind of this formation here. So you can see these formations take into account of both the intra-feature outline factors as well as the inter-feature outline factors. So we then conduct a random walk on this value graph, and the visiting probabilities of a particular specific node is equivalent to its value outlierness, because the edge here and the node properties here have already conveyed the information of outlierness. So by walking around, have a random walk process on this value graph, we can, when it converges, we can just simply use the stationary probabilities of these random walks as the value nodes value outlierness. So this is the traditional way to do the random walk. So previously we have this walking or transition probability matrix, and this part is the visiting probability vectors. So for a graph have n nodes, they will have n total number of cells in this vector will be n. And we introduce the damping factor here to guarantee the convergence of our algorithm CDRW. And this is the common way to guarantee the convergence of these random walks. So we also analyze is how fast the such kind of random walk will converge. The conversion rate here is basically determined by the properties of the value graph we construct. And we will show some results later that all those value graphs will have very small graph diameters and have very high large graph densities. Those two properties has a very good guarantee that our method here will have a very fast conversion rate. This is one result. We use the CBRW to have direct outline detection. So this part is setting the delta. So it's to setting the delta to 1 to all the delta. So basically, it only can consider the inter-feature outline factors. This one setting the E eta to 1. So this one basically consider only the intra-feature outline factors. So you can see the results. The original models here and the two variants of these models have substantially better performance than the traditional ones, and the one is the best is still goes to the full model. They models both of the inter-feature outline factors and also the intra-feature outline factors. And this is some results when using our method to do feature selection. So this CBWFS is our feature selection methods. So using in feature selection methods means that we use the values to calculate the outlines of each features, and then we have a ranking. This is a feature ranking based feature selection. So we will use top K features as the relevant features to go through all the features. You can see even we remove a very large percentage of features, our method still perform much better than the original one. This is partially due to those datasets have a large number of noisy features there. I will talk about the noisy feature issue in the later methods. So this is the graph diameter and clustering coefficient. You can see very small diameters and large clustering coefficient. These two properties guarantee that our methods have very good convergence rate. All of them converge within 100 iterations. Some of them converge very quickly within 20 iterations. And yes, this is a simple conclusions here. So we use the intra and interfeature outline factors to learn the value outlines. This enabled to have a very good modeling of the non-ID values. Two applications are obtained from mission result. Then another piece of work is specifically focusing on feature selection, but this feature selection is for outline detection. Feature selection for outline detection is a very special problem. You may search on the Google Scholar. There has been very limited work from this perspective. The challenge here is it is in unsupervised nature. It is very challenging to evaluate the relevant or the outlines of feature, and the complex feature interaction there also made the problem much more challenging. So the need for designing feature selection for outline detection is that because the one reason is the outlines are often masked as normal objects by noisy features. Noisy features here mean, simply put, is the one feature that in which the outlines contain frequent patterns, but the normal objects contain infrequent patterns or infrequent values. This just the inverse of what we hypothesis. We always assume the outlines contain infrequent values or rare values, but normal objects have contain frequent values or patterns. So this is in no features. This is the inverse case. Then we will have the framework here. So we working from the value levels up to the feature levels. We use similar methods to the previous word CDRW to have the value outlinings and analysis. After obtaining the value outlinings, by utilizing the value to feature interactions, we can infer the feature outlinings and build the feature graph. Having the feature graph, we can using many of the shelled graph mining methods to find a feature subset from the feature graph to use for the subsequent outline detection. So the instantiation of the framework called DSAFS is working as follows. So the value graph is quite similar to the previous work, and this helps us to capturing the concurrent red values, and the methods we map we derive a feature graph from this value graph is still very simple. So the simple way we use is just use the linear summation of the associated value pairs of any pair of features here. So given an example here, if it is F1 and F4, we will sum all the value pairs between these associates with these two features together as the edge weights in this feature graph. Because in the value graph, the edge weights has already indicated the outlineness, but sum them together for each pair of features in the feature graph. The edge weights here also indicate the outlineness of these two features, or in other words, the relevance of these two features to the outline detection task. So since we build a simple feature graph, this capturing only two-way feature interactions, but we can do a more complicated to extend to 10 tensor or even higher order feature interactions. After obtaining the feature graph, so we design these objective functions. The objective function here basically it says that we want to find a subset of S that maximize the average outlineness of any pairs of features in this feature subset. So it is a common way. It is also a popular objective functions in general feature selection. I mean the feature selection for classification or class territory. So the difference here we built on the feature graph, which conveys the outlineness of the features. And if you're familiar with the dense subgraph discovery, you can see this is equivalent to find the density subgraph out of the feature graph A. So this equivalence facilitates us to have very nice solutions to this problem. So the solution is a linear time greedy search, but have a very good approximation guarantee. It is a two approximation guarantee. And the search method is work in this way. So for given a graph, the first step is to find the node which has the smallest degree and remove it. And then go to the next stage to remove another node which have the smallest degree. So going through all the nodes until one node left. And we use the subgraph here, which has the largest subgraph density. The density is defined in this way. So such kind of density subgraph can be used as the following features outline detections. This is the evidence of our methods. We test our feature selection methods on 50 UCI datasets. This is some data indicators. We calculate how many noise features in those datasets. This is the redundancies indicators. The larger the value here, the more redundant this dataset. The size, the dimensionality, and the D prime is the features our method retained. You can see this is the reduction rate, which means we remove a very large percentage of features. On average, it remove about 50% features. But after removing such high percentage of features, it is impressive that we still have a very large AUC performance to 3 different types of outline detectors. This is the probability test-based methods. This is the information theory-based methods. This is the you can see the AUC improvement is substantial. And the runtime here is the SU denotes the speed up. And you can see some original data outline detectors, if their original time complexity is not that high, the speed up here is not very substantial, up to 2 orders of magnitude faster. But for the frequent pattern base, as you know, they are exponential to the dimension. So the speed up is up to 6 orders of magnitude fast. Yes, the conclusion is that the framework is very flexible. So other graph-based mining methods can also apply to the feature graph to do the feature selection for outline detector. As far as we know, this is the first method specific designed for unsupervised feature selection for outline detection. Although many work has been done for clustering or classification or regression. And our method is parameter free and retains 2 approximations to the optimal. Next, we introduce our recent work, which will be presented in the IIDness in a few days later. Is dealing with noise features, but in a very different ways. This is an example I made for the fraud detection. So we assume the rare patterns are outlined, but in order to this feature is the relevant features. So the outlines have rare values here. The non-outlines have high frequency values, but this is the noise features. So the outlines have infrequent values, but the normal objects have have infrequent values. This is the frequent values. This is what I mean the non-IID features. So the existing solution, including the work published in ICDM, is those selection other subspace based or feature selection. They are all filter based approaches, which means they made independent from the feature selection or subspace selection from the subsequent outline detection. As a result, the features retained may not be optimal to the subsequent OD methods. So our solution here is we explore the wrapper approaches, which enable us to have some simultaneous feature selection and outline detection. So the framework is look like this. So for datasets, input of feature subset, we will have outline scoring functions to assign a score to each object and have a ranking. After the ranking, we have a ranking evaluation functions to evaluate how the qualities of these outline rankings, and to output another feature subset and iteratively until we find the best feature subset. Because for a specific feature subset, we only have as one outline ranking. So if we obtain the best feature subset, we also obtain the best outline rankings. So the challenge here is how can we ensure the outline scoring efficiency? Because you can see from this iteration, we will need to go through many times of the outline scoring functions. If the scoring function efficiency is poor, it will be very costly. And another challenge here is how can we evaluate the ranking qualities without the class labels? So we are always working on the unsupervised case here. So I will introduce you briefly how we solve these two challenges. So these scoring functions need to be at least satisfy these two conditions. At least sufficiently resilient to the non-IID features, and you need to be very efficient. And we still utilize the homophilic couplings here. So I made the intuition more clear here. So the outline behaviors are often concurrent, but the non-IID behaviors, they are just all often randomly co-occurred. So based on these observations, we can simplify the CBRW to be an undirected value graph. So the benefit of undirected value graph is that the random walls on this such kind of graph will have very efficient corresponding solutions. So this will help us to have a very efficient initial value outline's estimations. And after this, so this step is the first stage to learn the homophilic couplings. And the second stage use any other methods to further estimate the value outlines. So this is the value outlines of U. This row is the point-wise mutual information between the U and V, which means the more correlated is the V to U, the more major influence this U's value outlines impact on the V. So if V is accompanied by a lot of highly outlying values, the V's outlines will be very high. Yes, this is the ranking evaluation. So this we create a soft pseudo class labels to do the objective functions, and we use the recursive backward feature elimination method to generate the feature subset. This is our process. I skip this to see some results. We also use quite a lot UCI datasets. So this is the noise levels. This is the reduction rate we obtained. So again, we have very huge feature reductions, but have very significant or substantial improvements over the existing state of the art, including our previous work. And these two, we compare with the two feature selection we designed for the previous IIDkai paper and ISBM paper. This is the IIDkai paper. This is the denote that we use the ISBM feature selection methods. So due to the filter-based approach properties, our method is simultaneous optimization. So the improvement is significant. This is the sensitivity to the K. Mostly stable, but may more advanced strategy need to taken. This is the scalability test. It's linear to the data size, projected to the dimensionality. Yeah, so source code will be made available here. Yes, I finished my turn here. Yeah, I give to.
Thank you very much. So, so in the next half hour also, so just briefly address three topics here. So one is about statistical learning. How can we incorporate a little bit more about the data into the statistical model? Just very brief here. So just to do the two pieces of work here. So one is that it's called mixed membership stochastic block model, and the idea here is that is to incorporate a coupler function into it. And so in your formula, some of you, I don't know whether you're familiar with the coupler. Coupler function has this kind of theory behind. See, you have like a joint distribution between the two hidden variable or random variable x and y, and you have the the marginal distribution is known like fx and gy, and then we can have a unique coupler and that can be equivalent to this kind of representation. So that's basically the coupler thing. And so there's another thing that is MMSB, and actually detects overlapping communities, and that could be for the for a fixed number of community or infinite. Yeah. So in our case, actually consider the infinite case. So the graphical model is like this. So it goes like a node I and j, and that a parent beta, and then that may follow or created from a so-called stick breaking construction process, and then got a triangle gamma, and then so you don't look at this part of the moment, just to the composite bit, and then you have in the community you have a sender and a receiver, and that connect two nodes I and j, right? And the model actually is to detect what so how this works, and in order to get a link between node I and j, which is observable, right? Okay, and that need to follow certain kind of binary distribution. This here we have to use a beta and binary distribution. So that's basically the MMSB model. So in our case, so what we did is that actually we changed this model and assume actually the node I and j, their their connection and they are this sender and the receiver, they are somehow correlated, right? And that correlation can be described by this copula, right? And then this is the function and the model. So basically, the C1 and C2, and just to define this stick process, stick breaking process, and assume this pi. So in a node I and J actually can be drawn or sampled from this judicially process with some parameter there. And the key thing we changed here in this basic MMSB is to add this part. So we assume that node I and J actually could belong to the same subclass. I mean community here, and then they belong to the same community, and they follow certain kind of distribution, and this distribution can be described by a common function, right? So that's basically the idea here, and then indicate actually, they are partially correlated, but certainly you can change the copula to, for the whole population, like use a Gaussian or something. In our case, we use the gamma, copula, and then partially correlated, right? And then you can solve this, do the inference like MC and C, and to find the parameter. So that's basically the key idea here. And then we create two model here. So one is actually to have a marginal conditional on this pi, which means the mixed membership distribution. And so it's got a copula based MMSB. Another one is that we actually have the marginal conditional on the UN way. That is actually the copula, decomposition, sort of like that. And we have two, the marginal distribution UN way. And and then the sampling will be different. And this one you sample actually pi as well as the sender and the receiver. And this one you sample UN way and then pi and also sender and receiver. So if you look at this the function, the performance of this one, the training error and test error and test log likelihood and AUC. So you can see here. So these two models actually can beat all other models on the data, except this one, this infinite mixed membership model. And but even the training error, so they got a lower, but actually our prediction is higher. So it somehow shows that incorporating this this node interaction or node relationship by copula actually contributed. So the one piece of work, and then another piece of work I just explain here is to incorporate the node information into the Bayesian non-parametric model, so the idea here is like this. So this is a basic MMSB model, and L is a latent feature relational model. So the idea is just like what I described earlier, but the only difference between these two models is this part. For the MMSB, you got the sender and receiver to describe the relation between the two nodes. And for the LFRM, you actually have this data node actually whether it belongs to a community K or not, right? So it's got a different things there, and the rest will be the same. So what we change here is we don't actually have this on this pi j and pi I sample from the judiciary process, okay? So we don't have this sample from the judiciary process just based on one parameter, will be like a gamma parameter basically from this beta. And so what we have is that we actually change that part. So essentially this part has been changed. The stick breaking process construction has been changed. So what we have is that we actually incorporate more observable information. So this node information for I, node information for J, and that could be related to node attributes like so whether the attributes has a value, and this converted to binary, and it got like a 1, otherwise it got a 0, something like that, right? So you got this binary representation of the node information. So that's one thing. The second thing that is we actually incorporate a zeta function that to replace the gamma, the one parameter digital process. And the role of this one is that is actually to is actually help the stick breaking construction. Actually, this one represents the contribution of the feature F, on the node I, right? So in terms of that community K, right? So then you can actually for all the features for that node and I and J, you can consider all of them, right? Okay. So this in the stick breaking construction actually has been changed. So that's the second thing. And then the third thing that when we change this stick breaking construction process and we generate the new weight for the membership indicators, pi I and pi j, and we've got a new weight help to adjust that. Okay, so this has been changed, and the rest will be the same. And then we actually incorporate this new mechanism into the MMSB and also LF, the latent feature relation model. And then we generate a node information based mixed membership model and node information based latent feature model. Okay, so let's see what will be the performance, and we test on two data sets, and you can see here, and these two models. And you see, and there's another one we create, and you see actually they actually always beat other model actually, but this one actually still quite good actually, but the AOC AOC is pretty good. So basically to see some of the improvement of these two models, right? So that's some of the recent work here, and for this two statistical model. And we actually work more on, which haven't been published, and some of the more work actually already finished, further working on how to encourage the behavior of the node and also the node interaction by incorporating the node information into the Bayesian non-parametric models, and to understand the behavior, the interaction between the nodes to informing the community. For both static and dynamic, and then we can use that for different purposes like link prediction, community detection, etc. So that's a very brief introduction of some of the work here. And then I quickly move to another topic related to behavior analytics, and this certainly is a very big topic. So I just that's one of the example here. So behavior is everywhere. So I just ignore this part. So in my case here, so the behavior actually we follow something like this. You got a behavior is described by, there's a subject and object here, and then you got time, place, and a particular action there. And even you can model the goal of behavior, the belief, the plan, the context, the status, and some constraints here to describe this behavior. So that's a behavior I have. I won't go detail to this. And then essentially follow that model. So what we have is that so for each behavior is actually can be described by a behavior vector. And in this vector, I got a multiple dimension now, and you got a time, space, action, etc. And that actually incorporates the behavior properties. And then sequence of behavior suddenly form a behavior sequence, right? And it's a vector-based behavior sequence. So using this kind of behavior representation, and we actually start to talk about global behavior analysis. And by the way, if you are interested in this, a lot of slides, and we create online, like 300 pages more than I think papers there. So you are in more detail. So for global behavior, so one way we can look at, is to look at from this perspective. You go to the I actors, like people, right, or like machine or whatever. So that's the subject, and then you go to the moment or maybe time window or time points, J max time points there, and the behavior actually of this group of people within this J max time point or time window, we can actually describe in terms of behavior feature matrix, right? In this behavior feature matrix, each element represents the behavior of a particular person at that moment. Okay, it's a vector. Okay. So then what we have is that we have to consider, for each person's behavior, which is, is horizontal, and there's the interaction between the behavior of this person, right? Like D11, D12, etc. And we have to model a relationship, with what do we call an behavior, the coupling here, the theta j, and to describe, the relation between them. And the second part is that it's for a time point or time window, which is vertically, we have to look at, okay, what is the relation between B1, for example, right? For the same time point or time window, right? And we have to model and find, another, relation, it's called an intercoupled relation, the eta I. And then, so the problem we have to address is that for the global behavior, actually we have to consider, okay, so what is within each person's behavior, the relationship we have to find is the theta, and then between the two people, at a different moment, the two people at the same moment, there's a eta function there as well to describe the relation, and then how they actually, this is theta for one person, and then eta for different person at the same time, how they actually group together. We have to learn this function here, right? And then finally the problem can actually be described as to get an objective function to describe that. So basically, the high level idea is that you got for one person's behavior, got their relationship to be described by theta j, and then the different people at the same moment, their interactions, behavior interaction, to be modeled by eta I, and then they group together for the whole team. So then the whole problem for group behavior analysis becoming a problem like this. Sorry, this is a problem definition. Something like this. We need to find an objective function that can, the G function that can satisfy certain kind of constraints, but also satisfy the constraints here is that we learn these two, relationship and also their grouping, their aggregation, and this aggregation satisfy certain kind of condition, and then we, try to approximate or solve this, loss objective function. So here, just like earlier, I think one of the audience asked a question here is that, so when you consider the relationship, complex relation like theta and eta, this is a horizontal and a vertical relation, and their integration, whether that could incorporate like, overfitting or some of the noise, those kind of things. Yes, actually, so we actually add the constraint here, which means actually, you will not incorporate everything. As, you probably have to do some, filtering, or optimization here. So that's the idea here, okay? So that's a high level idea. So then we see how we can use this to do something quite sophisticated. That is to identify a poor manipulation in stock market, in the real market, okay? So in stock market, what we often see is that the price sometimes, not often, sometimes you see the price actually goes up and then suddenly goes down, right? So what actually drives this price movement? This price movement in the market is more like exterior, right? It's exterior presentation. And then there's the internal driver. That's actually the trader's behavior represented by what? By their action. The price, the volume, those kind of things, and withdraw. Place an order, withdraw order, something like that, right? So for this particular case, maybe something like this. Initially, someone manipulator actually put a very big buy order there, and put a few big buy and then withdraw and then push the price up and mislead other people. And other traders actually started to come into the market and put more and more buy order and push the price up, and then suddenly there's a big sell order actually executed most of the best buys in the order book, right? And then the price starts to go down, right? So that's basically some of the manipulation work mechanism. So I mentioned that, so this is tick data, tick data in the stock exchange, and then this needs to be converted to see what is why these guys, from different directions buy and sell, they collaborate and, to push the price up, and this is something like price up here. And I just already mentioned we have to create a behavioral, sequence and a vector as well. So what do we have here is that we have multiple sequences that have buy and sell trade, and we have their relationship and also their behavioral properties like a price and volume and action. And how can we do that? So so one thing we can do here is that is to create a coupled heterogeneous model. So basically, you can have like a trade sequence and a buy and a sell sequence and a buy sequence as well. And for each time moment like a t-1, and we know they'll they may affect or be related to the next moment t's state. Like this buy may be related to sell here at t, right? And then t-1 trade maybe the execution of of two the two buy and sell, right? Okay. So this is basically a Markov assumption and the chain, right? And so then what we like to do is that, okay, so we go to the group behavior analysis to be modeled by coupled Markov model. This is called a straight chain here. And we've got a state here, and state represent a different the buy sell trade, okay? And then we have there's a hidden state, and then we have observation. Observation actually captures the behavior. In this case, the behavioral sequence, there are the properties of behavior. And then we have these interactions that coupling relation. So we just assume this Z actually capture this horizontal and vertical relation and their combination. So that's the assumption to use a coupled Markov model. And then you can build different models as well. You can build a relational probability tree model. You can build a relational Bayesian classifier model. So like this conditional probability model, and you can actually for trade, you can be represented by the conditional probability and the relational features as well, and to be represented by them. And so a lot of detail actually we ignore here. So if you like to know how actually the behavioral properties like price volume, how they actually be represented and mapped to the coupled model, you can read the papers. And show the result here. So you see, like we can have build a heterogeneous model for buy, heterogeneous model for trade, for buy, for sell, and then you can have another model actually just simply combine them, so like a linear combination. This is IHF model. But we can also build a coupled heterogeneous model actually consider their interactions, right? And we can also create an adaptive coupled heterogeneous model, which means the market is dynamic. How to make the model actually can be a little bit more adaptive to the market dynamic. So now we can compare the performance. So look at from the accuracy or the precision, whatever perspective, and you can see actually this consider the relation within and between behavior actually make more sense in this case. And we also look at, and then you can actually change the window size, because this work on the tick data, which means you've got probably thousands of probably dozens of millions of transactions and quite intensive, and build the time window like 30 minutes or 20 minutes to aggregate the behavior, and so that we can manage this better. Yeah, and then we actually compare, evaluate this from the business performance perspective, which means those people we initially identified, which likely, they collaborate in some way, whether they make more money, their abnormal return actually much higher, right? So this shows actually their abnormal return could be really high, and that actually indicated from business perspective this may be something important, right? Now we build other models as well, like what I just mentioned, relational probability tree and Bayesian classifier, etc., and see, to improve the model performance. So that's what we, some of the KDD paper, so if you are interested. And then I skip this document analysis, and you can find it from the slides, and then I move to another one, is vision, but I just very briefly, it's a IIII paper this year. So we have image here, so we have the medical image, got some of the regions here, and then you got the central point, central nodes there, got the neighborhood there, right? You can represent it this way. and also can create a cell as well. So the idea here is that we have, we create different kind of representation. As this different representation, and use that representation to capture the characteristic in this data, and then we build a joint matrix and to learn this. So how do we do that? So so what we have is that, okay, for the central nodes, and we calculate their distance, right? And also we have, for each central node, we got their neighborhood, right? So this one, we got neighborhood here. This is vertical, right? And this center, we got a vertical, we got the neighborhood as well, is a horizontal. And then we not only calculate their central node similarity and distance, but also their neighborhood similarity, right? And use a different way. And so one is to do the direct product with the kernel. Another one is to build a historical distance kernel as well. And then the third one is to do the max polling. And each of these kernel, actually, all these three, we try to capture their complexity in the data from both perspectives. So you got two components. One is actually between the center node, and another is between the neighborhood, right? So each of them actually work like that. And then we just build an objective function. It's basically to combine this matrix, and that actually it's got multiple P kernel, and find a way and to minimize it, and then this for the equivalent to this objective function with some of the constraints. Right? So then we actually build the handcrafted features, about 37 dimensional features, and also the deep learning based features of 64, and then we incorporate them into the model to do the image segmentation. And here to compare the different method, and this three created by different kind of matrix models, direct product, hospital distance, and this max fully, and then the combination of them, right? And compare with some of the existing methods like the CAN, etc. And you can see here clearly, this way to integrate them actually significantly beat other methods, right? And also you look at this ROC curve, this is ours, quite overwhelms the performance. And this is the actual image segmentation. So ours, you see, compared to other methods, is very clearly, segment the objects, and this is the convergence rate, quite efficient. Okay, so just for 1 more minute, okay, so I just summarize. So essentially, I think today is just some idea like non-ID, and the way we want to do is that, so we often see blind people cannot recognize elephant. So if this is if we create a learner, and we want the learner to recognize the elephant, and that's essentially non-ID. Why? Because we have very complex problem here. Doesn't matter whether it's big or small. We've got many parts, many source, many wheel, multiple tasks, multiple labels, etc. And just one perspective cannot really figure out the whole big picture. And we have to do is to think those parts, the coupling relationship between the parts and heterogeneity between parts, and how can we build a new model actually can represent the heterogeneity. Heterogeneity between the entity as well as the relation, right? So that's basically move from ID to non-ID. And in doing that, we have to consider the data non-IDness, we have to consider non-ID similarity, dissimilarity, build the matrix or measure, and to do the representation and build the objective function, and maybe a lot of perspective as well. And then the objective function will be different from this one, right? So you have to consider that, right? So that's basically the idea. And there are huge opportunity actually. So many things we did before seems like we could actually look at from another perspective, right? And that has actually driven us in the past few years to work more and more from as what I mentioned earlier, from different aspects, and the hierarchical thing as well, right? So that's basically the tutorial today. You got a lot of reference there, and you can download the slides from here or papers and give us comments. That's it. Any questions or any suggestions? Lunchtime, right? Okay. Okay. I really appreciate it and thank you guys. Thank you very much. Just enjoy KDB. All the best. Thank you.